Good morning, lads and ladies. Welcome back to college algebra. Today we're going to do a few things. We're going to spend a little more time talking about polynomials, and then we're also probably going to introduce and play a bit with rational functions. But before we do that, I want to spend just a second or two wrapping up the material on polynomials, kind of trying to make sure we're all on the same page there. And then towards the end of class, we are going to do a little activity. So let me go ahead and set the alarm for that, make sure we don't forget to do that. Let's see. 55 minutes. All right. So without further ado, here we go. I suppose we need to keep going. The other little bit of news here is that I think I finally got all the gradebook and exam stuff worked out. Unfortunately, your exams, the comments there and feedback that I'm giving you are typed in rather than like handwritten stuff that overlays your actual work. I generally don't find that the typed feedback is as helpful, but if you need clarification on any of that stuff, just let me know. So there's something there where like you want to see more detail, or you're curious what I meant with the comment, please don't hesitate to let me know, and we can talk about it either through email or Canvas or office hours. This is MAC1105, section number 015, which is college algebra. And the date today is the 17th of February, 2022. Today, we'll talk a little bit more about polynomials. And talk about rational functions. And then we have a little activity. So in case you haven't done it yet, please go ahead and download the attachment from the announcement this morning. Posted to Canvas here. If you go to Canvas, go to announcements, click on the one for today. There is an attachment there. It's labeled activity 3.5, and it's on proportionality. That's one of those topics where I find going back and kind of shoring things up is usually a good idea. I am doing something a little bit different with the homework this week. So because the polynomial homework and the rational function homework kind of connect together in a lot of ways, I thought it might be nice to have both of them open over the weekend so you can spend some time going back and forth if you want to. So you'll see here the polynomial homework, rather than being due today, is set to be due on the 22nd, along with the polynomial quiz, and so is the rational functions and radical function stuff. So we're going to play with this stuff today. And we'll pull a few problems out of here to work together. But before we do any of that, a little bit more on these polynomials. So last time we learned what a polynomial is. There's a formal definition and kind of an informal definition, and we saw that we can factor polynomials to try and find end behavior. What is this? This is not. No, this is the power function quiz. We can factor polynomials to try and find their x-intercepts, and we call those roots. There were a few problems, or a few kind of statements that I made as theorems or facts that I wanted to illustrate for you a little bit more. How do I keep clicking the wrong damn thing? Polynomial functions. Okay. That I wanted to illustrate for you, like that statement about the degree of a polynomial and how the degree of a polynomial can tell you the maximum number of roots. And then also this business with a function being even or odd. There is a connection between the stuff we were doing when we talked about power functions being even or odd, and polynomials being even or odd. So let's do that. Maybe we can begin by talking a little bit So degree, remember from the definition last time, is the largest power of x that shows up anywhere in that polynomial's expanded form. So if you have the polynomial fully multiplied out, the largest power of x is the degree. And there's a connection. So we have this fact from last time that a polynomial of degree n can have at most n roots. Right? So if you're looking at a polynomial of degree n and you know it's of degree n, then you can tell me right away that the graph crosses or touches the x-axis at most n times. Conversely, if you're looking at the graph of a polynomial, you can tell me the minimal degree for that polynomial, right? So this statement can kind of be interpreted two different ways. If the degree is n, then the number of roots is less than or equal to n. And that's the same thing as saying if the number of roots is n, then the degree is greater than or equal to n. Sure. So let me illustrate really quickly here with an example. Because the way we use this theorem is not usually in the forward direction, but it's in the backward direction, where I give you the graph and you tell me the lowest possible degree. So we're going to state the minimal degree each polynomial. And we're going to connect this then to something called multiplicities. So I'll graph a few polynomials here. Here's one we'll call P of X. The y-axis is the x-axis. We'll call this next guy Q of X. And then this last one, let's call this H of X. Okay. So for each of these graphs, you know that the function being graphed is a polynomial. So the fact above applies. I want you to tell me the smallest possible degree of that polynomial, meaning if you were to somehow conjure the algebra expression for this, have everything multiplied out and expanded, what is the largest possible power of x? And we want to be thinking about this fact that a polynomial of degree n can have at most n roots. In other words, the degree is always greater than or equal to the number of roots. It's the kind of other way to say this. And it's called the contrapositive. So looking at the graph of P here, P of X, how many roots does P have?
Three.
So we've got a root here. R1. Got a root here. Call it R2. I've got a root here. Call it R3. right? Each x-intercept is a root. So this guy has 3 roots. And since the degree is greater than or equal to the number of x-intercepts, aka roots, the degree here has to be at least 3. So the minimal degree is 3. It could be higher. It could be higher. And I'll explore with you a little bit how you can tell that in just a minute. In fact, when we get to h of x. But before we do that, let's try with q. So if we apply that same exact logic to the graph there for q of x, what do we find for the minimal degree?
4.
Yeah, this guy crosses the x-axis 4 times, right? There's a root here, a root here, there's a root here, and there's a root here. 4 roots, 4 x-intercepts means that the degree is at least 4, could be higher, but couldn't be smaller. Looking at h of x, I'll need you to think about not just that fact, but also about the end behavior. So if we count the number of roots, there's 1 here, and there's 1 here. Right here, the graph like kisses or bounces off the x-axis. Right here, the graph crosses the x-axis. But each of those is a root. Call this R1. Call this x-intercept right here R2. So based on the fact above, the degree here has to be at least 2. I claim that it is not possible for this to be the graph of a degree 2 polynomial. Why?
Because the root is odd.
Very good, very good. So 2 roots means that the degree is greater than or equal to 2. But also the end behavior going up on the left and down on the right tells us that the degree is odd. And if you put those 2 statements together, that the degree has to be at least 2, bigger than or equal to 2, and also odd, the smallest possible number that satisfies those 2 conditions is 3. 3 is the smallest odd number that is bigger than or equal to 2. So the minimal degree here is not 2, sorry, 3. Minimal degree is 3. And you notice something a little bit different about the behavior or the shape of the graph at this root compared to all the other x-intercepts here, right? Here the graph crosses, we go from positive to negative, we go from above to below. At all of these, the graph crosses the x-axis, goes from above to below or below to above. And the same is true here. But at this guy, the graph goes from below to below. Rather than crossing the x-axis, he just kind of bounces off of it. That's a behavior associated with something called a particular multiplicity. So this is the last kind of bit of material for the polynomial section, but it connects with the other stuff in a really beautiful way. So multiplicities of roots and the shape of the graph. I'll say recall that if x equals r is a root for the polynomial p of x, then x minus r is a factor of p of x. In fact, it goes both ways, right? If you know the roots, you know the factors. If you know the factors, you know the roots. So how do we find roots? We find roots by factoring. And if I wanted to construct a polynomial with certain roots, then I would do that by gluing together the factors that correspond to those roots. And I'll show an example like that. It's possible for a certain factor to show up more than once in the factored form of a polynomial. Consider, so let's write that down. It is possible for a given factor to occur more than once in the factored form of a polynomial. In fact, you've seen this before. When you get a quadratic and it factors as like x minus 2 times x minus 2, you can write that as x minus 2 all squared. That's what's going on, right? For example, I could have something like x plus 1 times x squared minus 1. And if I factor this a little bit further, that's x plus 1 times x minus 1 times x plus 1 using my difference of squares trick on the second piece. Remember that a squared minus b squared always factors as a minus b times a plus b. If I use that trick to continue factoring x squared minus 1, then I can rewrite that piece as x minus 1 times x plus 1. And now I've got these three chunks, three factors, all multiplied together. There's no rule that says they have to stay in that order, right? Like a times b times c is the same as a times c times b. As long as you keep the same factors and everything is multiplied, you can shuffle the order around. Multiplication is commutative. And then x plus 1 times x plus 1, just like x times x is x squared, x plus 1 times x plus 1 is x plus 1 squared. So this would be written as x plus 1 all squared times x minus 1. So when I say that a factor can occur more than once in the factored form, this is what I'm talking about. The factor x plus 1 shows up twice here. And I can put them together. The power you get here when you put those factors together is called the multiplicity of that factor, or the multiplicity of the root, really. So what are the roots here? Well, they're the numbers that make each of these factors 0. That second factor is equal to 0 when x minus 1 is 0. And this first factor is equal to 0 when x is negative 1. If you look at the x minus 1 factor, when there isn't a power written, of course, that means that thing is being raised to the power of 1. So this guy, we would say, has multiplicity 1. And the root x equals -1 has multiplicity 2. In other words, the multiplicity of a root is the power of the factor from which that root comes. And you have to have your polynomial fully factored out, right? I can't see in here from this statement that x plus 1 shows up to the power of 2. You need to actually factor it all the way out and then group the factors that have the same roots together. The multiplicity of a root affects the shape of the graph near that root. Basically, here's the idea. Basically, if you have a root of multiplicity m, then near that root, the graph will look like the function x to the m looks near the origin. The basic rule I need you to remember shape of the graph near the roots. If the multiplicity is odd, then the graph will cross the x-axis at x equals r. Now, we didn't even specify the name of the thing, just say graph will cross. And if the multiplicity is even, then the graph will bounce or kiss the x-axis. And that's what was going on in that third graph that I drew for you on the previous page, the graph of h of x. The first root, r1, was an odd multiplicity root, and the graph crossed there. The second root, r2, was an even multiplicity, and the graph bounced off the x-axis there. So, draw for you a nice big picture. Here's some polynomial. And these shapes can actually get kind of interesting. Let's see. Just to give you an idea what each of these can sort of look like. This would be the graph y equals p of x, where p is a polynomial. I'm going to identify each of those roots as having an even multiplicity or an odd multiplicity. And I'm going to go just a tiny bit further here for you. And I'll let you know kind of what is required and what is optional. First, let me just label each root. This is R1. This is R2. R3. This is R4. going to say the root and its multiplicity. So the multiplicity of the root R1, just based on the graph. What can you tell me about that?
It's got an odd multiplicity.
Gotta be odd. Yep. And the little bit of information I'm going to add for you here is that this is what a multiplicity 1 root looks like. You're not required to know this last part. But a multiplicity 1 root looks like just a straight cross, no funny curvy business at all, just straight through. R2, even or odd multiplicity.
Odd, I mean even.
Yeah, this has to be an even multiplicity because the graph is like bouncing off of or kissing the x-axis. So this is an even multiplicity. And you notice if I zoom in right here and I just forget about the rest of the graph, I just pay attention to this part of the graph, doesn't that kind of look like x squared? If I cover up everything else, doesn't that kind of look like a quadratic nearby there? That's what a multiplicity 2 root looks like. Again, the blue is not stuff that I'm going to test you on. The black is stuff that I am going to test you on. The root R3, even or odd multiplicity?
Odd.
Yeah, the graph crosses the x-axis here, right? We go from above to below, from above to below. So because we cross, we know that this has to be an odd multiplicity root. And if you look at the graph of x cubed, it has that kind of squiggle shape here, right? Actually, this particular one looks more like negative x cubed, but that kind of S-curve shape, right? This, if you just look nearby, looks a lot like this does. And that's what a multiplicity 3 root looks like. And the root R4, because we bounce off the x-axis here, we do not cross. This must be an even multiplicity root. And if you compare that to x to the 4, it's kind of like that parabola shape, but it's flattened out along the butt. Kind of like that parabola shape, but it's flattened out, kind of squished against the x-axis. That's what a multiplicity 4 root looks like. And the beauty of this is you could tell me what the degree of this polynomial is. If you know the multiplicities, this is the last fact, and then we'll look at some example problems where we actually have to solve some things. Sort of concept here. The degree is always what you get when you add up the multiplicities. It's the sum, SUM, meaning what we get when we add up of all the multiplicities. So I claim that the degree of this polynomial, this was a multiplicity 1, this is a multiplicity 2, this is a multiplicity 3, this was multiplicity 4, would be 1 plus 2, which is 3, plus 3 is 6, plus 4 is 10. This is a degree 10 polynomial. And I've got 0 like numbers I can look at, right? I don't have any bits of the algebra there. Nowhere have I even written the letter x besides labeling the x-axis. But even without that, I can tell you the degree of this polynomial. And notice that the end behavior matches with that claim, right? The end behavior being down on both sides requires the degree to be even. And you'll find that these two rules always work well together. They never contradict each other, which is pretty neat. Okay. I'd like to look at a couple problems related to something like this. So first, find a polynomial with the roots x equals 3 with multiplicity 2, x equals 0 with multiplicity, say, 3, and x equals -2 with multiplicity 1. And let's additionally require that p of 0, oh no, I already specified p of 0. Okay, having end behavior, no. Let's do it like this now. Let's say having p of 1 isn't a root, right? P of 1 equal to 5. So problems like these are quite common. Someone gives you the roots and they ask you to come up with the polynomial. This last little bit of information, that p of 1 is 5, is what we're going to use to determine the lead coefficient. So if you think back to those quadratic problems where you were given the vertex and then a point, or two of the two roots and then a point, you would use the vertex or the two roots to kind of set up the general polynomial. And then you had to use that extra bit of information, either the y-intercept or some other point, to solve for the lead coefficient a. Same sort of thing. Just now we have a bigger polynomial. It's not a quadratic, but it's literally the same field. From each root, we get a factor. So roots and factors. I know x equals 3 is a root, which tells me that x minus 3 must be a factor. I'm told that x equals 0 is a root. So I'll write it like this: x minus 0 is a factor. And I'm told that x equals -2 is a root. And that tells me that x plus 2 must be a factor. And then I was told that the root x equals 3 is multiplicity 2. That means that factor has to have this power. I was told that the root at x equals 0 is multiplicity 3. That means this factor must have that power. And I was told that the root -2 is of multiplicity 1. That means this guy has that power, or you could just not write the 1. And this is almost enough to completely determine the polynomial. So all this stuff together tells me that p of x must be some constant times the product of these factors. X minus 3 squared, x minus 0 cubed, and x plus 2 to the 1. Now, this can be written a little more nicely, right? X minus 0 is just x, so this is x cubed. X plus 2 to the 1 is just x plus 2. What I would not do is multiply this out. Well, there's no need for me to multiply this out. But I can write it a little more nicely as ax cubed times x minus 3 squared times x plus 2. Right, the x minus 0 is just x, so x minus 0 cubed is just x cubed, and it looks nicer to put that term out front. And then x plus 2 to the 1, nobody writes the 1. Questions up to here? If I wanted to know the degree of this polynomial, one option would be to multiply everything out and then take the biggest power of x. But holy shit, that's a lot of work, right? I am far too lazy for that crap. But if you add up the multiplicities, 2 plus 3 is 5 plus 1 is 6, boom, it's a degree 6 polynomial. Tells you right away that if you multiplied everything out, the highest power of x would be x to the 6. Cool. We still have this to account for. And I still have this to find. Right? I still don't know the lead coefficient. So I haven't answered the question yet. In order to find this lead coefficient, I need to use this information. Namely, this says when you plug 1 in for x, the whole thing should be equal to 5. So since p of 1 is equal to 5, we have, let's see, imagine I plug 1 in for x over here. That would be p of 1. Right? If I plug a 1 in for x here, that's p of 1, which I know is 5. And if I plug 1 in over here, I get a times 1 cubed times 1 minus 3 squared times 1 plus 2. And I can use this to solve for a. And as you do this, follow your order of operations, right? So let's clean up inside the parentheses first. One cubed is just 1. 1 minus 3 is negative 2, so this is negative 2 squared. 1 plus 2 is 3. So this is the same. 5 is equal to a times 1 times 4 times 3, right? Negative 2 squared is 4. 1 times 4 times 3 is 12. So 5 is equal to 12a. And dividing both sides by 12, you get 5/12 is a. Now we have finished solving the problem. We just have to write down the answer. Therefore, p of x is a, which is 5/12 times x cubed times x minus 3 squared times x plus 2. And that's your final answer. Cool stuff, right? There are a lot of variations on problems like these, but they all go the same way. You get the information about the roots and their multiplicities. Use those to figure out the factors. Then you set up your polynomial. The thing people often forget is to put in this lead coefficient, right? There are many polynomials with these factors, infinitely many, in fact. And in order to say which one for sure it is you're talking about, you have to put in this lead coefficient and then at the end solve for it. There was a problem that was requested in the chat, so I want to take a look at that. And that was in the polynomial homework. that this guy?
Yes.
Okay. Yeah, this is actually a fun one, and it's related to what we were saying a moment ago, that the degree is the sum of the multiplicities. So we want to determine the end behavior. P of x equals negative 3x times x minus 2 times x plus 1 times x plus 2 quantity squared. Okay. In order to sort out the end behavior, I need to know the degree and the sign of the lead coefficient. Those are the two things I need. So I need the degree and lead coefficient. The lead coefficient is the same in every form of the polynomial, right? In the factored form of the polynomial, in the expanded form of the polynomial. I should say those are the only two forms we deal with. So this polynomial is in factored form, right? This has been factored. It is written as a product of factors. And in that form here, we have a negative 3 out front. So the lead coefficient is negative 3. The degree is going to be the sum of the multiplicities. So let's come in here and add our multiplicities. This x is like x minus 0 to the 1. This x minus 2 is x minus 2 to the 1. X plus 1 is x plus 1 to the 1. And x plus 2 squared is x plus 2 squared. So multiplicity 1, multiplicity 1, multiplicity 1, multiplicity 2, which means that our degree is 1 plus 1 plus 1 plus 2, which is 5. The degree is the which is 1 plus 1 plus 1 plus 2, which is, and that degree is odd. This lead coefficient is negative. So if I have an odd degree polynomial with a negative lead coefficient, it must look something like this, that end behavior. And what's even cooler, we could actually use all this information to draw a beautiful graph of this polynomial. But first, let's just point out, this is the end behavior, right? Up on the left, down on the right, because the lead coefficient is negative and the degree is odd. My roots would be negative 2, negative 1, 0, and positive 2. At negative 2, we're going to bounce. At negative 1, we're going to cross. At positive 2, we're going to bounce. Oh, 0, yeah. At 0, we're going to cross, and at 2, we're going to cross. So this guy actually looks like something like this. Just come down here. Right. From the roots and the multiplicity, we could sketch a good graph, but they just wanted the end behavior. And if you wanted this in the goes to or arrow notation, we say as x goes to negative infinity, y goes to positive infinity, right? So as we go very, very far off to the left, the graph goes up. And as x goes to positive infinity, as we run off to the right, the graph goes down. So y goes to negative infinity. You can get that in either way or any of those ways. Questions here? Let me see how I'm doing for time. 16. Okay. don't think there's anything else we need to say about these polynomials. I think we're in pretty good shape here. The coefficient, yeah. Complete factored expression. Yeah. So local mins, local maxes, global mins, global maxes. These are things that we've talked about before. I don't think we need to reiterate all of that. We've talked about even and odd functions before. Yeah. Okay. Maybe before I depart from polynomial land, I'll give you one more fun fact. Even functions. These are ones where f of negative x is the same as f of x have y-axis symmetry. And odd functions these are ones where f of negative x is negative f of x. Their graphs have origin symmetry. And we introduced even functions and odd functions when we talked about power functions, just straight up power functions. I mentioned back then that other functions can also be even or odd, right? Indeed, polynomials can be even or odd. Trig functions, if you've heard of those, can be even or odd. Rational functions, which we're going to start talking about soon, can be both even or odd. There's a fun fact or trick. A polynomial will be an even function if and only if all the powers of x are even. And this includes the idea that the constant term is an even power of x. Right? The constant term is really like something times x to the 0. Remember when we talked about degree 0 polynomials? Constant are polynomials, the degree is 0. So that constant term in any polynomial we think of as being an even power of x. A polynomial will be an odd function if and only if all the powers of x are odd. And you could include here and the constant term is 0, or there is no constant term, right? Because that constant term would count as an even power of x. That would ruin this for an odd polynomial. So it's a real quick way to determine whether a polynomial is even or odd is to look and see, are all the powers of x even? Or are all the powers of x odd? Of course, if you have the graphs, you can rely on the symmetry interpretation. And if you have an algebraic expression that is kind of limited for whatever reason, you can't tell what all the powers of x are, then you can use the algebraic definition. Okay, that's enough on this. We do have to at least define what rational functions are. And since we have the activity to go as well, let me go ahead and get to that. Rational functions are ratios or fractions where the top and bottom are both polynomials. That's all. That's all. They're fractions made up of polynomials. So for example, f of x equals x plus 1 over x squared plus 9 is a rational function. G of x equals x squared plus 2x plus 1 over x minus 3 squared times x plus 7 is a rational function. H of x equals the square root of x minus 2 over x squared plus 3x plus 9. This is not a rational function. Because the top is not a polynomial. Right, so remember those kind of subtle rules for figuring out whether something is or is not a polynomial. You just need to apply those rules separately to the top and to the bottom. If both of those things turn out to be polynomials, then you've got a rational function. If either of them turns out to not be a polynomial, then the thing you're looking at is not a rational function. We've actually looked at some graphs of rational functions before. A number of those power functions we were playing with were rational functions. And the main reason, well, one of the reasons we talk about rational functions at this point in the class is to discuss a little bit more carefully those things that we drew in as dotted lines when we drew like 1 over x and 1 over x squared, asymptotes. And asymptotes can come in 2 flavors, vertical and horizontal. If you think about the graph, y equals 1 over x. It looks like this. And those dotted lines indicate that the graph continues in this way, getting closer and closer and closer and closer to that dotted line. The vertical dotted line here, we would call a vertical asymptote. And the equation of that vertical line is going to be x equals some constant, right? Because vertical lines are always x equals a constant. In this case, the x value everywhere along this vertical line is 0. So we would say that the vertical asymptote for this guy is the line x equals 0. The dotted horizontal line here, we call a horizontal asymptote. Horizontal lines are always y equals a constant, and in this case, every point along this line has y value 0. This is the horizontal line, y equals 0. There is a connection between the vertical asymptote and the domain. Vertical asymptotes show up because the output from the function is getting really, really big. it's tending to infinity. That's what we would say, right? Like if you're looking at the points along this graph, as you get closer and closer to this vertical asymptote, the y values are blowing up. Desmos is a little better for illustrating this sort of thing. Okay. So if we zoom out a little bit and kind of look at this graph, as we get closer and closer to that vertical asymptote, the red graph, those y values are blowing up to infinity. And the same thing is true over here. Those y values are going way, way, way down. And they go all the way down to negative infinity. And you notice that no matter how far you look, no matter where you look, there's no point on the red graph whose x value is 0. So I'm going to push the rational function homework forward a little bit, I think, give you a few things, just one thing here. I'm going to tell you how to find vertical asymptotes, and then we're going to switch over to doing the activity. What I said is that vertical asymptotes are connected to the domain. So we talked about how to find domains very generally at the beginning of the semester. One of your big domain rules is that the bottom of a fraction can never be 0. Well, these rational functions, they're all big fractions. And they all have polynomials in the bottom. So if you want to find the domain, you set the bottom to 0. Those would be the numbers, the solutions to that equation would be the numbers that are not in the domain. Those also tell you the vertical asymptotes. So the domain is all real numbers except those which make the bottom 0. And the vertical asymptotes, which I'm going to abbreviate here as VA, are the lines x equals C, where C makes the bottom 0. So in other words, you get the domain and the vertical asymptotes at the same time. All right, if I hand you a rational function, I ask you, find me the domain. I hand you a rational function, I say, find me the vertical asymptotes. I'm really asking you to do the same thing. I'm asking you to set the bottom equal to 0. Okay, that's the trick. Now the answers will be different, right? The domain is all real numbers except for those which make the bottom 0. So after you set the bottom equal to 0 and solve that equation, you're going to get some numbers out. Like here, if I set the bottom equal to 0, the solution is x equals 0. So my domain is everything except 0, which would be negative infinity up to 0, union with 0 to infinity. And my vertical asymptote is x equals 0, because that's what makes the bottom 0. We will play more with this next Tuesday, but for now we need to switch over to the activity. So I am going to put you guys into some breakout rooms. Please open up that activity. Before I put you in the breakout rooms, again, remember, if you haven't downloaded this, you can click here in the announcements on Canvas. This is what the activity looks like. These are proportionality problems. So we've had a little bit of time to stew on these. Hopefully everybody is done with that proportionality homework at this point. I just want to work a couple of these together, give you guys a chance to bounce ideas off of each other and ask questions. The first problem says, on planet Euler, the time t it takes for an object to fall is directly proportional to the square root of the distance h. Suppose it takes 3 seconds for the object to fall 16 feet. Tell me the equation that relates t and h. Find the constant of proportionality. And then tell me how long would it take that same object, or any object really, to fall from 100 feet. That's our first question there. So t is directly proportional to the square root of h. It takes 3 seconds to fall 16 feet. Write an equation relating t to h. Find the constant of proportionality. That equation will have a constant. And then tell me how long it's going to take to fall from 100 feet. And you can round your answer to the nearest tenth to 1 decimal place. Second problem, there's only 2. A student's score on the final exam is inversely proportional to the number of alcohol drinks they consumed the week before. Last semester, the student consumed 15 drinks in the week before the exam and scored 60%. What score can they expect if they consume 25 drinks? So same sort of thing. We have an inverse proportionality relationship now. Here, you have to define the variables. You have to choose what you want to call the variables. I haven't done it for you. Set up an equation, solve for the constant of proportionality, and then you can answer this question. All right, so do the first problem first. It'll help kind of warm you up. I'm going to go ahead and sort you into breakout rooms. And I will come in and check on you guys as we go. So let's do forms. Okay, once you get the invite, please go ahead and join that breakout room. I'll come in and ask you some questions and make sure we're all participating. Wow. Gabriella, Ariane, you guys here? And just to be clear, I can't give you credit for the activity unless you join the room and work on the problems with your group mates. Okay. Alrighty, guys. Is there anything we'd like to talk about? Anything with those problems that feels a little shaky? How's it coming along?
I mean, we just started. I don't know. Can you guys hear me?
Yeah, I can hear you. Sorry, I was trying to pull it up.
Oh, okay. Sorry, I was trying to make sure that we could all hear each other.
Okay. Yeah, Kylie says she can hear you okay.
Did anybody have it printed out, or should I?
I'm not going to collect the physical activity. If you want to just work the problems on your own paper, that's okay, as long as you guys work the problems.
Okay.
Cole, are you with us here?
Okay. So, problem 1. I need to write an equation that relates t to h. So
And the trick is they told us that t is directly proportional to the square root of h. That's where I'll begin. I'll give you guys a second to think on it. I know we just started. I'll come back in a few seconds.
okay. Okay.
No stress. Hey guys, I know we're just getting started, but is there anything you'd like to ask about? How's it going so far?
Pretty good.
On that problem 1, do we have an idea for what equation we could start with?
Is it D equals TH squared?
Let me see. So D equals TH squared. It's not that complicated. It's not that complicated. So I can turn on my screen share here. The only variables we have to worry about are T and H. And they told us that the time T is directly proportional to the square root of H. So H is the distance. We don't need a second variable for that distance. You could just stick with T and H. And then the trick is that if I know A is directly proportional to B, this means A is equal to some constant times B. And so here they told us that T is directly proportional to not H, but the square root of H. And that would tell me that T is equal to some constant times the square root of H. So if we start there, if we start with that equation, then we can try to work out that constant using the next bit of information from the problem, that it takes 3 seconds to fall 16 feet. So one of those, the 3 or the 16, one is a time T, and the other one is a height H. So if you plug in the time and that height, then you'll be able to solve for K, and that'll knock out those first 2 parts. So let's take that, see if we can get through those, and then I'll come back and check on part 3 in a minute, okay?
Thank you.
Yeah, of course. Hey guys, how's it going so far?
We're
Good.
douche.
Assessing.
Doing good?
We're trying.
Okay. Yeah, no, that's good. That's all we asked for. Is there any particular part where I could give you a little nudge?
Can
for
you just tell us
the-
if the first one's right? Like if we got the equation right?
Yeah, what you got?
We have the square root of 16 equals K parentheses 3.
That sounds pretty close. I can show you, let me show you how I would set this up.
Okay.
So we know that, sorry, cover this up real quick. We know that if we say A is directly proportional to B, that means A is equal to some constant times B. So for the very first part, we're just looking for the equation like this, but with the values or the variables that they gave us here. So they told us that the time T is directly proportional to the square root of H. So that means A here is like T, and B here is like the square root of H. So for part 1, we're just looking for this equation. T is equal to to K times the square root of H. And then for part 2, it looks like that was kind of where you guys were, is that if it takes 3 seconds, that's a time. So that's a value we'd plug in for T. It takes 3 seconds to fall 16 feet. So that's a height. So that's what we'd plug in for H. So we would say 3 is equal to K times the square root of 16. That would be the first step for part 2. And then we can use this to solve for K. So 3 is just 3. The square root of 16 is 4. And then if I divide both sides by 4, we get the constant of proportionality is 3/4. So then let's take this and see if we can use it to answer this last bit of stuff here. So I would take this constant K, and plug it back in here. Now I'd make sure to write down this equation without the variables plugged in before trying to go to the next step, because this is kind of like, once you get here, you can do anything you want with this problem. And that's a nice place to be. So having solved for k, we plug it back into our proportionality equation, and that gives us this. And now if I wanted to know how long it takes to fall from any height, we could plug that in. Or if someone told me the time it took for an object to fall, I could plug that in here and solve to find the height.
That makes a lot more sense. Thank you.
Cool. Yeah, these problems are always weird at first. So I like the idea of being able to work a few of them together. I'm going to go check. I got one other room to check in on, and I'll come back through and we can talk about the next one. Okay. Hey guys.
You got the constant as 9.
Me too.
And the first problem?
The second problem.
Ooh, let me see. That may be the case. So in the second problem, oh, if I let S be the score, drinks, we have this. So we've got 60 is K times.
I got he would get a 36 on his next score.
So that sounds plausible. Can I ask how you got that constant?
We did the 0.6 or 0.60 equals C over 15, multiplied the 15 over the 0.6, and we got the constant as 9.
Very good. Okay, yeah, that sounds very good. So we have something looking like this, right? I used S and D for score and drinks, but you can use whatever variables you want. So this is that inverse proportionality. And then we can plug in. We know that the score was 60% when we had 15 drinks. And then we can multiply that over. And so K equals 9 is good. And then how did we finish it up?
You solve for Y or the S.
Yeah, and you can use whatever variables you want. There's nothing wrong with using X and Y. So we're told that homeboy's going to drink 25 drinks before he goes to take his final. And we want to see what happens. So we plug in 25 here.
Score went down.
Yeah, and that's kind of the point of the inverse proportionality versus direct proportionality. If two things are inversely proportional, then as one goes up, the other will go down. So we went from drinking 15 beers before the test to drinking 25 beers before the test. And naturally, that would result in a decreased score. I don't have the calculator open, but we can go ahead and see what this comes out to.
It's
So
0.36.
very good. Yeah, excellent. So that would be 36%. Nicely done, guys. Is there anything you wanted to ask about from either of these?
Will you
The
just go
top
over
one.
the answers at the top? Yeah.
Say that one more time. I'm sorry.
You go over the answers to the first question.
Oh, yeah. Yeah, sure. There you go. So if we say that A is directly proportional to B, that always means that A is equal to some constant times B. And here we're told that the time t is directly proportional to the square root of h. So we'd start with this equation right here, t equals some constant times square root of h. And then they told us that it takes 3 seconds to fall from a height of 16 feet. So I can plug in 3 for the time and 16 for the height. And that gives me this, which I can try to solve for k. The square root of 16 is 4. So we get 3 equals k times 4. Divide both sides by 4. And we get 3/4 is k. Then we can plug that in. So this k is 3/4. We know that now. And then we could answer any sort of question we wanted. And the last thing they asked us for here was the time it takes to fall from 100 feet. So from 100 feet, the time would be 3/4 times the square root of 100. And the square root of 100 is 10, so that's 3/4 times 10. And there's a few ways to do this, right? 3/4 is 0.75, so that's 0.75 times 10. Which would be 7.5 seconds.
That's what we got.
Excellent.
We were just confused about if we would square root that 100 or not.
Yeah, definitely we do. So kind of the place we start is that first equation right here, the t equals k root h. This is kind of our guiding light through the whole problem. Anytime we're kind of wondering what to do, we always come back to this guy and ask, well, what do I know? And what do I need to look for? So in that last part, we already knew what k was. We plugged that in. And then they asked us, well, what's the time from height 100? So we can plug in to that equation also 100 for the height. But very nicely done, guys. All right, I'm going to go ahead and pull us back into the main session and we'll wrap up.
All right.
All righty, Zoom takes about a minute to close these breakout rooms. So while we're waiting for everybody to trickle back in, is there anything that you guys wanted to ask about from those? I can show you here what my solutions to these look like. So for that first problem, we know that if somebody tells you that A is directly proportional to B, that means A is equal to some constant times B. And there they told us, we just had to be careful with the wording, that the time t is directly proportional to the square root of the height h. So that means that t must be equal to some constant times the square root of the height. Then they went on to tell us that it takes 3 seconds, so that's something we can plug in for time, to fall from 16 feet. That's something we plug in for h. And this will allow us to solve for k. So 3 is equal to k times the square root of 16. Square root of 16 is 4. We can divide both sides by 4 and get k is 3/4. From there, we can plug that 3/4 in for k. And once you have this kind of master equation with the constant plugged in, you could do anything you want. You can tell me how long it will take to fall from any height. You can tell me, if you know the time, how high up the object was. And they asked you, how long will it take to fall from 100 feet? So we plug in 100 for h. Here, so we get t equals 3/4 times the square root of 100, just plugging in 100 for h. Square root of 100 is 10, so that's 3/4 times 10. 3/4 is 0.75, so 0.75 times 10 is 7.5 seconds. The other problem we were told that the score, so I used S for score and D for drinks, the score on the test is inversely proportional to the number of drinks. So that means S is equal to some constant times not D, but 1 over D. Then they told us that we scored 60% having had 15 drinks that week. So we can plug in 60 or 0.6 for S, if you want to write it as a decimal, and 15 for D. And this will allow us to solve for K. If we multiply both sides by 15, we get K is 15 times 0.6, which would be 9. Then they asked if dude has 25 drinks in the week before his test, what score can he expect? Well, that means we're going to plug in 25 for D and see what S comes out to. So I take this relationship with K plugged in, right? This is this equation, just plugging in the K value that we found. And then I could plug in 25 for D. So I get S equals 9 times 1/25, which is about 0.36 or 36%. These are both pretty classic problems. The next activity we're going to do has to do with power functions and that whole multiplicities of roots for polynomials. So that's where we're going to go. And then we'll talk more about rational functions next week. I am going to extend that rational function homework a little bit, so don't panic about that. Make sure you get the polynomial homework done and then take a peek at the rational function stuff. See what you can do based on what we talked about today. And on Tuesday of next week, we'll do more of that. All right. Take care, guys.